Welcome to the deep dive. Today we're tackling something I think a lot of us have run into, those really complex back-end workflows.
Oh, yeah. The kind that starts simple, maybe, but then grows into, well, let's just say spaghetti code feels like an understatement sometimes.
Exactly, tangled conditional logic, status flags everywhere. It
Wow.
just gets hard to follow, hard to change without breaking something.
And it's not just about looking messy, is it? It makes the system fragile. Debugging becomes a nightmare, and you start losing confidence that it actually works correctly in all cases.
Totally. So we've been digging into something that promises to bring some structure to that chaos. Spring StateMachine, or SSM, we're looking specifically at version 4.
Right. The idea is it's a framework within the Spring ecosystem specifically designed to help manage these complex processes in a much cleaner, more organized way.
Think of it like defining a clear roadmap for your process instead of just a bunch of branching paths that you hope connect correctly. Explicit stages, explicit transitions.
And it's current tech too. Version 4.0.0 is the stable release as of late 2023, running on Spring Framework 6.x and needing Java 8 or higher. So it fits right into modern Spring setups.
Now, the core idea here isn't exactly brand new. It's built on the concept of a finite state machine, an FSM.
Which is basically just a model where something can only be in one specific state at a time, right?
Uh,
And it moves between these states based on triggers like events or timers.
exactly. And what's interesting is how old this idea is, like predating Java even. It's a fundamental concept for modeling sequences.
It is very robust, very well understood principles. Spring State Machine just gives us a really powerful way to apply those FSM principles within a Spring application.
So for this deep dive, you've pulled together a lot of great material. Our mission really is to unpack how SSM helps us manage that complexity.
Yeah, looking at how it handles asynchronous stuff, how it ensures consistency, how we can model those long-running back-end processes.
Right. We want to distill the key takeaways so everyone listening can quickly get a sense of its value and, how it actually works under the hood.
Sounds good.
Okay, let's dive in. Starting with the absolute basics, states. In SSM terms, what exactly is a state?
Well, at its core, a state is just a specific condition or status in the life cycle of your process.
Mm.
It's a stable point where the system is waiting for something to
A
happen.
distinct phase,
Oh.
okay? And every process needs a beginning, right?
Absolutely.
Yeah.
You have to have an initial state. That's the entry point where the state machine starts its journey. You configure it really simply just using .initial.
Straightforward. And if there's a start, there must be an end.
Yep. There's the end state, sometimes called a terminate pseudo-state. Reaching an end state means that part of the machine, or maybe the whole thing, has finished its work.
How do we define those?
With dot. Simple again. And when the main machine hits an end state, assuming all its parts are done, the process usually stops. It gives you a clear definition of completion.
Okay, start and end points, clear. What about the states in between? Are they all just simple states?
No. You have simple states, which are, well, simple, no nesting. But then you have composite or hierarchical states. These are really powerful
How so?
because they let you embed other state machines inside them. It's like creating layers of abstraction. You can group related logic together.
Oh, interesting, like folders within folders.
Exactly like that. Helps manage complexity. You configure these using multiple .with states blocks and link them with .parent.
Okay, nested states for organization. You also mentioned regions. What are those?
Regions are parts of a state machine, either within a composite state or at the top level, that run independently, in parallel. Think of them like separate tracks running side by side.
Orthogonal, you mean?
Precisely. Each region has its own current state and processes transitions independently. Super useful for modeling concurrent tasks, like maybe processing payment and checking inventory at the same time for an order.
Ah, okay. Parallel processing within the same workflow. How do you set those up?
They can sometimes be implicit if a parent state has multiple initial substates, or you can explicitly name them using .region type.
Got it. So states define where we are, what actually makes the machine move. That's events, yeah.
Exactly. Events are the triggers. They're the things that happen, maybe a user action, a message arriving, a timer firing, that cause the state machine to try to transition.
And how are these typically represented?
In SSM, it's really common and recommended to use Java enums for events. Gives you type safety, which is great. Avoids typos, messing things up.
Makes sense. Can events carry data? Like if I need to pass an order ID when an order received event happens?
Yes, absolutely. Events can carry payloads. You usually do this using Spring Messaging message objects. The event itself can be the payload, and you can stick extra data, like that order ID, into the message headers.
Okay, so events trigger changes and can bring data along. Now, the actual movement itself, the path from one state to another, that's a transition.
Yep. A transition defines that directed link between a source state and a target state, triggered by a specific event.
Are there different kinds?
Primarily, yes. The most common is an external transition. When this happens, the machine exits the source state, runs any transition logic, and then enters the target state.
So there are actions involved at each step.
Potentially, yes. Exit actions for the source state, actions on the transition itself, and entry actions for the target state. It's a full handoff. You set these up with
Does the transition enter?
Got it. What if I just want to react to an event but stay put? Like update a timestamp while remaining logged in.
Ah, that's an internal transition. It lets you run an action in response to an event without leaving and re-entering the current state. Perfect for those kinds of updates or logging actions that don't change the fundamental state. You use the dot with internal for those?
External for a full change, internal for reacting in place. What about local transitions? You mentioned those briefly. Right. Local transitions are specific to those hierarchical composite states. They're like external transitions. But if the source and target are both inside the same composite state, a local transition won't trigger the exit and entry actions of the parent composite state.
Oh, okay. So it's movement within the nested structure without disturbing the parent.
Exactly. Keeps the transition contained within that sublevel. Good for moving between steps inside a larger phase. Just always worth double-checking the docs for the exact behavior, as details can sometimes evolve.
Good tip. Okay, states, events, transitions. Now, you mentioned some fancier transition types, these pseudo-states. They sound powerful for handling more complex logic. Let's unpack those. First one was choice.
Right. Choice sitter states are basically for dynamic conditional branching. Think if-else, if-else, but built into your state machine flow.
How does it work?
A choice state has one incoming transition, but multiple outgoing ones. Each outgoing transition has a guard condition. The machine evaluates the guards in order and takes the first one that's true. If none are true, you usually have a default else transition.
Like a decision point based on current conditions. Okay. How is junction different?
Junction is similar. It also uses guards for conditional outgoing transitions. But the key difference is a junction can have multiple incoming transitions.
Ah, so it can merge paths before making a conditional split.
Precisely.
Yeah.
It acts as both a merge point and a conditional branching point. Several paths can lead into it, and then it decides where to go next based on guards.
Choice. Single entry conditional exit. Junction. Multiple entry conditional exit. Got it. What if I need to kick off several things in parallel? That sounds like fork.
That's exactly fork.
Yeah.
A fork pseudo-state takes one incoming transition and splits it into multiple outgoing transitions. Each of those then typically leads to the initial state of a different parallel region.
So one event triggers the fork, and suddenly the machine is active in multiple regions simultaneously.
Yep. That's how you initiate parallel work streams within your state machine.
Super useful. And then, naturally, you need to bring those parallel paths back together. Is that join?
Yes. Join is the counterpart to fork. It merges transitions coming from multiple parallel regions back into a single path.
Does it wait for all of them?
It has to. The transition out of the join only fires once all the source regions connected to it have reached the state leading into the join. It's a synchronization point.
Waits for everyone to finish before proceeding. Makes sense. What about entry and exit points?
Those give you more control over entering and leaving composite states. Instead of always entering at the initial substate or exiting from wherever you happen to be, you can define named entry-exit points on the boundary.
So you can jump into or out of a nested structure at a specific spot.
Exactly. Gives you more flexibility for connecting complex hierarchies, maybe bypassing certain substates sometimes. Use dot with entry and a dot with exit to define them.
More precise connections. And the last one was history. That sounds useful for user interactions.
History states are great. They remember the last active substate within a composite state. So if you transition out of the composite state and later transition back to the history state, the machine automatically resumes in the substate you left off in.
Instead of just going back to the beginning of that composite
Right.
state.
Perfect for things like multi-step forms, where a user might navigate away and come back, keeps their progress. There's shadow history, just the direct substate, and deep history remembers nested substates too. Can add a bit of complexity to track though.
Remembering where you were, very useful. Okay, we've covered states, transitions, pseudo-states. But what about the actual work, the things we need the system to do? That's where actions come in, right?
Absolutely. Actions are where the real business logic hooks in. They're the executable code snippets that run at various points during the state machine's operation.
And how do you typically implement them in Spring?
usually as Spring Beans. You implement the Action SE interface. This means you can easily inject other services, repositories, whatever you need, right into your action logic using standard Spring dependency injection. Or, for very simple things, you can sometimes use speak-heal expressions.
Okay. And actions can run at different times, like when entering or exiting a state.
Yes, you have state entry actions, which run automatically when a state is entered, good for setup, logging, notifications,
Makes sense.
and state exit actions, which run when you leave a state. Good for cleanup, persisting data from that state.
How are these configured?
Usually in the StateMachine state configurer using methods like state entry and state exit, or sometimes directly within the .state definition itself. Then there are also state do actions. These run while the machine is in a specific state. Think of ongoing activities.
Like a background process tied to that state.
Kind of, yeah. But importantly, if a transition occurs out of that state, the do action can be interrupted. You configure these with state do no.
Okay, entry for setup, exit for cleanup, do for ongoing work. What about actions tied specifically to the movement between states?
Those are transition actions. They execute during the transition itself after any guards pass, but before the target state's entry actions run.
And where do you define those?
Directly on the transition definition in the StateMachine transition configure using .action, action bean. Good for logging the transition event itself or updating a timestamp related to the change.
Okay. And you mentioned error handling earlier. Can we define specific actions for when things go wrong?
Yes, that's a key feature for robustness. You can define error handling actions. If an exception occurs during a regular action, entry, exit, do, or transition, a designated error action can be executed.
How does that work?
When you configure your primary action, you can often provide a second action bean as the error handler, like .action, primary action, error action, or .state entry, state, primary action, error action. It keeps the error logic separate from the main path logic.
Nice, dedicated error paths. Now, before any transition actually happens, you mentioned guards. These are the gatekeepers, determining if a transition is even allowed.
Exactly. Guards are Boolean conditions. They run before a transition is attempted. If a transition has a guard, that guard must evaluate to true for the transition to proceed.
So they implement the conditional logic.
Precisely.
Yeah.
They decide if the state change occurs based on the current context, maybe data in the event message, or something in the state machine's own memory. If the guard returns false, the transition is blocked. The machine stays put.
How are guards implemented? Similar to actions.
Very similar. Typically as Spring Beans implementing the guards, a interface, so they can also use dependency injection. Or, again, simple conditions can sometimes use SPL expressions. You configure them on transitions using .guard or .guard expression.
Okay, so the guard is the check before the transition, and the action is the work during or around the transition. That distinction seems really important.
It's fundamental. Guards decide if, actions decide what to do once a decision is made. Guards shouldn't have side effects. They just evaluate conditions. Actions perform the side effects, database updates, API calls, etc. Keeping that separation makes the whole thing much clearer.
Decision logic versus execution logic. Got it. That clarifies the roles nicely. Now, we've covered a lot of concepts. Maybe just a quick recap of the main pieces we've discussed. You mentioned a summary table.
Yeah, just to tie it together, we have states, initial, end, simple composite regions, configured in the StateMachine state configurer. We have events triggering changes. Transitions, external, internal, local, define the paths between states, configured in the StateMachine transition configurer. Actions, entry, exit, do, transition, error, perform the work. Configured in both state and transition configurers. Guards make the decisions before transitions, configured in the transition configurer. And finally, the pseudo-states, choice, junction, fork, join, etc., provide advanced routing, also in the transition configurer.
Okay, that's a solid overview of the building blocks. Now, how do we actually put this all together in code? Let's talk about configuring a state machine using Java.
Right. The main way, and generally the most recommended for type safety, is using Java configuration with annotations and these adapter classes Spring provides.
Okay, and what's the first step? Enabling the feature.
Yes. You use one of two main annotations on a Spring a configuration class. There's @EnableStateMachine. This sets up and registers a singleton state machine bean in your application.
One machine for the whole app.
Usually, yes. The alternative is @EnableStateMachineFactory. You use this when you need multiple independent instances of the same state machine definition.
Like one state machine per user order.
Exactly. Instead of a single bean, this gives you a state machine factory bean. You inject the factory into your services and then use it to create new state machine instances on demand, usually giving each one a unique ID.
So add enable state machine for one global machine, at enable state machine factory for creating many isolated ones. Makes sense. You mentioned adapter class.
Yeah, they just make the configuration code a bit cleaner.
Mm.
If you're using Java enums for your states and events, which is common, you extend enum state machine configure adapters E.
And if you're using strings or something else.
Then you'd use the more generic state machine configure adapters E. Either way, you extend the adapter and override its configure methods to define your machine.
Okay, let's look at those configure methods. Which one handles defining the states themselves?
That's configure, state machine state configures, E states. Inside this method, you tell Spring about all your possible states.
Oh.
If using enums, you can do something like states.withStates, .initial mystates.start.states, enumset.all4, mystates.class.end, mystates.innd. You define the initial state, list all states, define end states.
And hierarchies and regions.
Yep, you configure hierarchies here too using .parent to link substates to their parent. And you define regions using .region. This is also where you attach those state entry, exit, and do actions using methods like .entry, undo, and .exit, .ownEntry.
Okay, so the state configurer handles the structure and state-specific actions. What about the paths between them, the transitions?
For that, you override configure, the state machine transition configure SE transitions. This is where you define all the ways the machine can move.
Using things like with external and with internal?
Exactly. With external source state A's target state B event event X, or with internal source event action event X, or with internal source state C event Y action. You chain these calls together.
And this is also where you add actions and guards to the transitions.
Yes. Use action bean or action bean error action bean for transition actions, and guard or guard expression for the guards.
And the pseudo states like choice and fork?
Them too. You configure with choice, with torque, with join within this transition configure method. It defines all the dynamic movement logic.
Right. Are there any other general configuration settings?
There's one more main one. Configure. State machine configuration. Configure is SE-CANSIG. This is for global machine settings.
Like?
Things like whether the machine should start automatically on an application startup using .auto startup, mostly relevant for singleton machines. You could register global listeners here using .listener bean to monitor everything happening. You can set a specific task executor for async stuff and define policies for handling transition conflicts if multiple could fire at once.
Okay, global behavior settings. You shared a simple Java config example. Can we walk through that quickly?
Sure. It's a basic example, maybe state A, state B, state TD, and event .ty. The config class has at configuration and at enable state machine, so a singleton. It extends enum state machine configure adapter.
What does it configure?
The state configure sets state A as initial, registers all three. The transition configure defines a transition from A to B on event X, maybe with a logging action, and another from B to C on event Y. The general config might set auto startup and register basic listener. Then your main app code would auto-wire the state machine bean and send events to see it change state.
A simple illustration of the pieces working together. You did mention, though, that Java config can get wordy for complex machines.
It definitely can. Especially the transition configuration with nested actions and guards can become quite long and potentially hard to read for very large state machines. That's a trade-off.
But the advantage is the tight Spring integration.
Absolutely. Because your actions and guards are just Spring beans, you get full dependency injection. You can easily, at auto-wired, your services, repositories, whatever you need, right into them. That's a huge plus for connecting the state machine to your actual business logic cleanly.
Okay, Java config. Type safe, integrated, potentially verbose. Got it. Now let's pivot to applying this. How do we actually model our business workflows using these state machine concepts?
It starts with analyzing your process. You need to clearly identify the distinct, stable states your business entity goes through. Think about an order. Placed, paid, processing, shipped, canceled. Those are your states.
Okay, identify the states. Then what?
Then identify the events that cause changes between those states. Payment received, order validated, item shipped, order canceled.
Right.
Then map out the allowed transitions. Can you go from placed to shipped directly? Probably not. Define the valid paths. Then add the conditions. Is payment confirmed? Is stock available?
The rules for the transitions.
Exactly. And finally, figure out the actions. What needs to happen when you enter processing? Maybe call the warehouse API. What happens during the transition to shipped? Update the database, send an email.
So it's a direct mapping Business stages to states, triggers to events, rules to transitions guards, and tasks to actions. Seems much more structured.
It really is. And as you said, the actions, Action S e-beans, become the place where you put the actual work. Calling services, talking to databases, interacting with APIs, transforming data.
Instead of having all that logic tangled up in some giant Eiffel's block and a service method.
Precisely. The state machine manages the flow, the state, while the actions perform the work for each step. It breaks down complexity enormously compared to just using Boolean flags or status strings scattered everywhere. The state becomes explicit and managed.
And because actions and guards are beans, we can reuse them, right? DRY principle.
Absolutely. Got a common logging action, make it a bean, inject it wherever needed. Got a standard validation guard, same thing. Define it once, use it in multiple transitions. Much cleaner, less duplication, easier to maintain.
Makes sense. You also mentioned the state machine often acts as an orchestrator.
Yeah, especially in more complex systems. The state machine itself might not do all the heavy lifting. It manages the state and decides what happens next, but the actions it triggers often delegate the actual work to dedicated service beans.
So the state machine directs the traffic, tells the actions, do this now, and the actions call the appropriate services.
Exactly. The state machine orchestrates the overall process flow, while specialized services handle the specific business logic implementations. It promotes a really nice separation of concerns.
Good architectural pattern. Now, workflows often need data. Intermediate results, IDs, flags. How do we manage that within the state machine? You mentioned state context and extended state. Let's start with state context.
Right. State context, E, is an object that gets passed into your action and guard methods. Think of it as a snapshot of everything happening right now in the state machine.
What kind of information does it hold?
Lots of useful stuff. Access to the state machine instance itself, the message that triggered the current event, including headers and payload, the transition being processed, source and target states, the current execution stage, and importantly, it gives you access to the extended state.
Okay, so state context is the current situation report. And inside it is this extended state. What's that for?
Extended state is basically a map object attached to each individual state machine instance. Its whole purpose is to store workflow-specific variables.
Like what kind of variables?
Anything relevant to that specific workflow run. Counters, intermediate calculation results, flags set by one action to be checked by a later guard, maybe an external transaction ID, data you need to carry along the process for that instance.
So it avoids having to create tons of extra states just to represent slightly different data conditions.
Exactly. It's for dynamic, instance-specific context data.
How do we use it in actions or guards?
You get it from the state context, .context.getExtendedState. Then you can interact with it like a map. Use .getVariables.putKey value to store things, and .getVariables.getKey to retrieve them. There's also a type-safe getKey class method, which is usually better.
A key value store tied to the machine instance. And since action methods return void, this extended state is the main way to pass data between steps in the same workflow.
Pretty much, yeah. One action does some work, puts a result in extended state. A later action or guard retrieves that result using the same key and uses it. That's the primary mechanism for sharing data within a single state machine's execution flow.
Makes sense. Are there any important things to watch out for when using extended state?
Definitely. First, scope. Remember, it's tied to one state machine instance. If you're using a singleton machine at enable state machine, different concurrent requests will be messing with the same extended state. That's usually bad.
Leads to race conditions. So that's why at enable state machine factory is crucial for concurrent workflows.
Exactly. The factory ensures each workflow gets its own isolated state machine instance with its own private extended state.
Okay, what else?
Persistence. When you use state machine persister to save the machine state, the extended state variables are typically saved along with it. This is good for resuming workflows.
But any downsides?
We'll try not to store huge objects directly in extended state. It can bloat the persisted context and impact performance or memory. Better to store identifiers, like an order ID, and have your actions fetch the full data from a database or cache when needed.
Store IDs, fetch details on demand. Good advice. Okay, that covers data management. Let's talk about designing for reuse. We've mentioned reusing actions and guards as beans and using the factory. What other patterns does SSM offer?
Well, beyond reusing beans and the factory pattern, you can also use the state machine builder for more programmatic, maybe dynamic creation of machines if needed outside the standard Spring config lifecycle.
Okay.
And we talked about hierarchical states and regions. Designing complex parts of your workflow as self-contained composite states definitely promotes modularity and conceptual reuse.
Encapsulating sub-processes. Makes sense. Are there ways to reuse entire state machine definitions?
Yes, two main ways. First is submachine references. You can define a state in one machine that actually delegates its behavior entirely to a separate, independent state machine definition.
So one machine calls another.
Pretty much. The main machine enters the submachine state, the submachine runs, and when it finishes, control returns to the main machine. Great for encapsulating complex, reusable stateful logic.
Interesting. And the other way?
Repository-based configurations. This is more dynamic. Instead of defining your state machine in Java code, you store the configuration itself, states, transitions, action references, in an external store, like a database using Spring Data repositories.
And load it at runtime.
Exactly. Allows you to change workflows without redeploying code and makes it easier to share or template workflow definitions. More setup, but very flexible.
So lots of options for reuse, from simple beans to embedding entire machines or loading definitions dynamically. And the choice between singleton and factory remains pretty fundamental.
Absolutely. Singleton is simpler for global state. Factory is essential for concurrent, isolated workflows. And then you have the trade-offs between Java config, type safe, static, repository config, dynamic, runtime overhead, maybe even UML modeling, visual. Choose based on your needs.
Okay, let's get really practical. We looked at the concepts. Now let's walk through that consolidated job example you mentioned, the order processing workflow using Spring Boot and SSM v4.
Right, so first up, project dependencies. In your Maven pom.xml or Gradle build file, you need the basic Spring Boot starter and, crucially, Spring StateMachine starter version 4.0. Make sure the versions align with your Spring Boot version, usually Boot 3.x for SSM 4.x.
Standard Spring Boot setup plus the state machine starter. Got it. Then the states and events.
Yep, defined as simple Java enums for clarity and type safety. Order states might have submitted, payment pending, paid, validation pending, shipped, canceled.
Okay, clear stages.
And order events could be receive payment, validate order, ship order, cancel order, the actions that trigger state changes.
Enums defined. What about the main configuration class? Order state machine config.java.
Right. It's annotated with @configuration, and since we're dealing with potentially many orders, at enable state machine factory. It likely extends enum state machine configure adapter.
And the configure methods.
Inside configure state machine configuration configure, we'd probably set auto startup false because we'll create and start machines per order. We'd also register our state machine listener adapter bean here via .listener.
Okay. What about states?
In configure, state machine state configure, we define submitted as .initial, list all other order states, and mark shipped and canceled as .states. We might also attach an action directly here, like state entry, order states .validation pending, validate order action.
Triggering validation automatically when entering that state.
Nice. And the transitions.
That's in configure, state machine transition configure. We define multiple external transitions. For example, submitted to payment pending on receive payment. Maybe with .action, log transition action, .action, store payment action.
Okay.
Then maybe payment pending to paid also on receive payment, but this time with a .guard, payment confirmed guard, plus the actions. Then paid to validation pending on validate order, and validation pending to shipped on ship order, guarded by .guard, order validated guard. Plus crucial cancellation transitions from various states like submitted, payment pending, to canceled on the cancel order event.
Covering the main flow and cancellations, you mentioned a listener bean. Yeah. The state machine listener adapter bean. It would override methods like state changed, event node accepted, extended state change to simply log what's happening with the state machine. Super helpful for debugging.
Visibility into the machine's operations. And the action beans themselves.
Right. Log transition action would just log the machine ID and the transition. Store payment add action would grab a payment ID from the event message headers using the state context and put it into the extended state.
Storing data passed with the event.
Exactly. And validate order action, triggered on entry to validation pending, would simulate validation logic. Maybe store a Boolean as validated result in extended state, and perhaps conditionally trigger the next event if validation passes, though often a separate process might monitor that flag.
Okay, actions doing logging, data handling, and business logic. What about the guard beans?
The example had two. Payment confirmed guard would check the event message headers for a payment confirmed flag. Order validated guard would check the extended state for that is validated variable we just stored. They control whether transitions like moving to paid or shipped are allowed, enforcing the business rules. Finally, how does the application code, like an order service, interact with all this?
The order service would be annotated with @service and @autowired, the state machine factory. It needs methods like createOrder, ordered, which uses the factory to get a new machine instance, starts it, maybe caches it, keyed by ordered for demo, or persists its context.
But,
Then methods like receive ordered payment, ship order,
okay.
cancel order. These methods first retrieve the correct state machine instance for that ordered, using a helper method like getStateMachineOrdered, which checks the cache or simulates loading from persistence.
Retrieves the specific machine for that order.
Right. Then it sends the relevant event using statemachine.sendEvent. For receive payment, it would send order events receive payment, possibly putting the payment head in the message headers.
And the trigger.
The sendEvent helper method would also likely simulate persisting the machine's updated state and extended state after the event is processed, and maybe remove the machine from the cache if it reaches an end state like shipped or canceled. Managing the lifecycle and persistence. Wow, that example really ties everything together. Factory, config, actions, guards, extended state, listeners, service interaction.
Yeah, it shows how all the pieces fit into a practical, albeit simplified, workflow.
Okay, great example. Now let's zoom out again. Where else, besides order processing, does Spring StateMachine really shine? What are common backend use cases?
Oh, there are quite a few where it's a really good fit because of that inherent statefulness and the need for structured transitions.
Like what? We mentioned order processing already. What about background jobs or task management?
Definitely. Think of multi-step batch processing or even complex DAGs, directed acyclic graphs. You can model each step or task as a state. Pending, running, completed, failed.
Yeah.
Events would be start task, task assess, task failure.
What features would be useful there?
Actions would run the actual task logic. Guards could handle dependencies or retry conditions. Fork join pseudo-states are perfect for managing parallel tasks in a DAG. Persistence is crucial for resilience and checkpointing. The tasks recipe in the docs covers this.
Okay, task execution. What about things like web wizards or multi-step forms?
Yeah, guiding a user through a sequence. States represent the steps. Step 1, Step 2, review, submitted. Events are next, previous, submit. Actions handle validation per step, saving data. Guards ensure steps are completed correctly before proceeding. You'd likely use a session-scoped state machine instance per user.
Right. How about controlling devices, like in IoT?
Perfect fit. Devices often have very distinct states: idle, active, error, sleeping. Events are sensor readings, commands, user input. Actions interact with hardware or communication protocols. History states could remember the last mode after a restart. The washer and turnstile samples show device control examples.
Interesting. What about more workflow-centric things like content moderation or approvals?
Absolutely. Content moderation. States like pending review, approved, rejected, flagged. Events like submit, approve, reject. Actions assign reviewers, update status, send notifications. Guards enforce policies.
Similar for user account lifecycles.
Exactly. States like registered, email verified, active, suspended, closed. Events like verify email, login success, suspend account. Action send emails, update status, manage permissions. Security integration becomes important here, controlling who can trigger which events. SSM has features for that, shown in the security sample.
So the common thread seems to be processes with clear, distinct stages, event-driven changes, maybe asynchronous parts, and where explicitly tracking the state adds real value.
Precisely. If you have those characteristics, SSM is likely a strong contender. If it's just simple, stateless request response, it's probably overkill.
Good summary. We've covered a ton. Are there any final, maybe more advanced considerations people should be aware of as they adopt SSM for production systems?
Yeah, a few things come to mind as you scale up. Persistence is key for anything non-trivial. We mentioned state machine persister and implementations for JPA, Redis, MongoDB. You need a strategy for saving and restoring the state machine context, state plus extended state, so workflows survive restarts.
Makes sense. What else?
Testing. Don't forget testing. The Spring StateMachine test module provides helpers to test your configurations and logic, often without needing the full Spring context, which speeds things up.
Good testing support is crucial.
Monitoring and tracing. In production, you need visibility. Integration with Spring Boot Actuator lets you expose metrics. You can trace state changes. The Spring StateMachine Auto Configure module helps here.
Observability. Important.
Security. We touched on it, but at Enable State Machine Security lets you integrate with Spring Security to apply role-based or expression-based constraints on who can trigger events or transitions. Very important for sensitive workflows.
Okay, and for distributed systems.
If you need to coordinate state across multiple application instances in a cluster, there's support for distributed state machines, often using something like Zookeeper for coordination. That's definitely an advanced topic. but the capabilities there.
Persistence, testing, monitoring security, distributed coordination. Sounds like it's ready for serious enterprise use.
It really is. It's a mature framework designed to handle these real-world back-end complexities within Spring.
Well, this has been an incredibly thorough deep dive into Spring StateMachine v4. We've gone from the basics right through to advanced production considerations. It really seems like a powerful tool for bringing structure and clarity to complex back-end logic.
Absolutely. That structured, event-driven approach is a significant step up from trying to manage complex state with just conditional logic and flags. It leads to more maintainable, testable, and understandable code.
The benefits: clarity, maintainability, consistency, managing complexity, reusing logic seem really compelling.
You really are, especially once your workflows reach a certain level of intricacy.
So for everyone listening, if you're wrestling with those tangled, stateful back-end processes, if you're dealing with complex asynchronous flows, or if your conditional logic is just getting out of hand, Spring State Machine is definitely something you should look into.
I'd agree. There's a bit of a learning curve, sure, but the payoff in terms of cleaner, more robust systems can be substantial in the long run.
Maybe, mastering state machines is like gaining a new kind of superpower for building solid, understandable applications. We definitely encourage you to check out the official docs and the samples we mentioned to really get your hands dirty. Thanks for joining us on this deep dive.